Okay, so to be able to look at our different acceleration cases, we do actually need to understand the concept of the chain rule. So the chain rule comes from calculus, and we're just going to briefly cover it like in a few seconds. But the idea behind it is you're going to have a function, and within that function, what you're inputting into that function is another function. So f is a function of g, and g is a function of f. So let's just write that out. F is a function of g. So f depends on g. So when g changes, f changes. So f is going to change with respect to g. And then g is a function of x, which means g is going to change with respect to x. And that's going to be important. That's like the fundamental behind the scenes aspect of this. I'm not going to go into the full math, but I am going to just briefly connect the dots. So those two pieces are super important. So if I am actually asking about the change in f, I have to consider, because it's with respect to the change in g, I have to consider the change in g with respect to x. So if I have, and in this case, we're going to have df, let's not do it like that, f prime. I have to look at the derivative of f with respect to g. So when I'm looking at this, I am looking at the inside. So g, that's the input. I'm looking at the input. So I'm taking the function and deriving it with respect to its input. And then I'm looking at how the input changes. So the inside function, and now it changes with respect to its input. And we just multiply them together because the change is multiplicative. And that's where the whole chain idea comes from. And again, I'm not doing all the mathematics behind this. I'm just doing like a quick connect the dots situation. So making the colors match. The first one, it's the outside function with respect to the inside function. And it's the inside function with respect to the actual input. So this is going to be important for us because now we're going to look at our acceleration. And our acceleration can be either a function of time, a function of velocity, or a function of position. And that's if you're looking in one dimension cases. And yeah, we are looking at it in one dimension cases. Now, when it is case one, which is acceleration is a function of time, that one's kind of straightforward because we know our definition of acceleration is just dv dt. Velocity with respect to time. So the rate of change of velocity with respect to time. So that's our standard definition that you should know. So that's a definition. And then if you want to solve for velocity, if acceleration is constant or dependent on time, in this case, acceleration is dependent on time, we're going to have at is equal to dv dt. We can separate the variables since acceleration is dependent on time. It goes with the dt part, and the dv chills on its own side. And then because they're separated, we can just take the integral on both sides with respect to their initial and whatever condition you're trying to solve kind of thing. Right now, I'm just going to leave it as indefinite. That's like a straightforward one. But if it is case two, okay, case two is also kind of straightforward. If we are just trying to solve for velocity with respect to time, So in case 2, we're going to have AV is equal to dv dt. And then the first thing you're going to do is, if you bring the dt across and then you have the dv there, you can't stop there because you have v sitting here. And remember, you want to separate the variables. So this v, because acceleration is dependent on v, it needs to go to the other side. So we're going to have dt is equal to 1 over a, which is a function of v dv, and then we can integrate both sides. And again, you will put in all your information that is connected to your problem. So those two are kind of straightforward. Case 3 is where it gets a bit fun, because if it is case 3, and we need more space for this, so let's move everything across. We're going to have AS is equal to dv dt. And at this moment in time, you'll notice you have an S sitting in front there, and that S doesn't connect to either the V or the T. It's a completely different variable. So you have to consider things now. And you have to consider that, hey, isn't S a function of time? So S is a function of time. So we actually have A, S, T. So when we're looking at that, we're actually looking at A and then S with T as a function there. So we want our derivative side to represent that, function within a function situation. So we're going to then use our chain rule to do that. So our dv dt is actually going to be, in this case, dv ds ds dt. So it's considering the fact that we are going to have and technically here we have our velocity is going to be a function of position, but position is a function of time. And then we're going to use that to get to our acceleration. Because remember, our acceleration is a rate of change of velocity. So then we take the derivative of the velocity in this format to get to our acceleration and the one that we want. But obviously we are solving for our velocity here, so we're doing the integrals. So when we're doing this, we are taking this part and we're going to sub it in there and try and clean it up a bit. So let's go do that. So let's just move that across. So we're going to have AS is equal to dv dt. The moment we see that and we have S featuring here and it doesn't feature up here or below here, we are going to consider our representation of our chain rule and what we're actually looking at. And we're going to sub it in. So the easiest way to do this is just think about the fact, if S is there, we want to bring in derivative with respect to S. So we're going to have dv ds and then ds dt. And we can say that because going back to what we just did over here, we had that v is a function of s and s is a function of time. So then if we take the derivative of v, we're going to have dv ds and ds dt. So we can do that from there. And then I'm just going to bring this as down. We can simplify it. So we're going to simplify this one. So we still have the as. I'm doing this in multiple steps. The dv over ds stays. We want to try and see if we can get rid of the thing with the t in it, because t is not showing up on this side. And we can do that because we know that ds dt is just velocity. And then we also know that these are commutative, so we can move these two around, make things neater. So we have as is equal to v dv ds. We can bring the ds across. I don't know, that's bad math, just go with me here. ds v dv. and then we can integrate both sides. Okay, so you have your three cases. The first two are kind of straightforward as long as you're trying to work out velocity with respect to time. Case 2, there is a special one if you want to work out velocity with respect to position. So remember that you can actually use the chain rule in case 2 if your answer you want velocity with respect to position to come out. And then you have case 3, which is where you're using your chain rule. And case 2, where you want velocity with respect to position to come out, same process as case 3. So let's just quickly do that. You would have AV, you have dv dt, but if you want v as a function of s to come out, you're going to replace this with dv ds, and then the ds dt to have AV there. Then you're going to have AV dv ds v, and again, just you can switch them around, it's fine. AV ds, you can't leave it like that, but again, I'm doing 100 steps unnecessarily to show you. And because the v needs to be with the dv, because remember you're separating the variables, you need it to go that side. So then you're going to have ds, and then you're going to have bad math, it's divided by that. So you're going to have v over AV dv, and now you can integrate both sides. So that's just a special option for case 2. And that's if you want velocity as a function of distance to come out. Okay, so let's just zoom out and recap. We're going to use our chain rule when it comes to our acceleration cases, specific acceleration cases. So our chain rule is basically, if you take the derivative of f, you want to find the rate of change of f. It's the rate of change of f with respect to its inner function, then multiplied by the rate of change of the inner function with respect to its input. Then you have your 3 acceleration cases. A is a function of t. That's kind of straightforward, it's straight from the definition. You should know your definition by now. Acceleration is dv dt. And then you can solve for velocity by separating the variables and taking the integral. And then you're going to have case 2, AV. AV is pretty straightforward. And then you're going to have case 3, where you have to use the chain rule.